All right, welcome back to AI for Healthcare. I hope you're having an amazing time so far. Our next speaker is Houmanfar. She is the VP of Machine Learning Products at integrate.ai. Please join me in welcoming Ro to our virtual stage.
Hello, everyone. Thank you for joining. Today, we will talk about private AI and its impact on healthcare. Data science and machine learning have shown a lot of promise for advancements in healthcare. You probably have all heard the success stories related to breast cancer diagnosis using medical imaging data, where the algorithm surpasses any human in diagnosis and advancements. You've also probably heard the advancements related to COVID, diagnosis, vaccination, and spread models. Machine learning cannot be effective without rich and relevant data. In the majority of healthcare use cases, the relevant data is patient-level data, and that is sensitive. Up until very recently, protecting the data has been equal to locking the data away, and therefore most use cases don't even see the light of day. You're all probably familiar with this diagram because it shows the different components of the ML system. I'm going to use this to anchor us in the problem and solution landscape. There are three main pieces to the system: data, machine learning artifacts, things like parameters and gradients, and last but not least, results and trained models. In traditional data sharing, a data owner needs to give direct access to the data. Without additional systems, there is nothing that stops full access or usage of the data. In this setup, data sharing means data custodians lose control over their data. And that is why you see a lot of time spent on data anonymization and onerous processes. The machine learning field has advanced to allow extraction of value without jeopardizing data. Privacy-preserving machine learning addresses who can access and modify the different components of an ML pipeline and how they can use them and what they can learn from them. There are many techniques that fit under the landscape of private ML. You probably have heard one or more of these names: homomorphic encryption, secure multi-party computation, and the list goes on. The reason for a variety of techniques is that there is no silver bullet. There is no one solution that is best suited to protect intentional or non-intentional wrongful access, usage, modification, or learning of the components in an ML system. They each have their pros and cons. For this presentation, we're going to reduce the scope. We're going to focus on machine learning models and the sharing of those and what is involved in sharing of those. And we're going to be talking in an additive format, although each of these technologies can be used separately or combined. Okay, let's anchor back on the ML components. We're going to look at technologies that protect some aspect of model training and the resultant artifacts in a multi-party machine learning system. Let's start with federated learning. Federated learning is a distributed approach which allows training of models without moving data from their sources. The system allows training of models that are local, so the nodes, and coordinates the different nodes to share the model parameters. This allows the system to get a better model that uses all of this information, but it doesn't allow the data access and usage to be wider than what the machine learning task is. And in this way, it restricts that access. Data is not shared and the data owner maintains full control. The con is that the training models in this distributed way can be a tricky task because it requires learning and debugging on top of data that cannot be accessed. Next, we have differential privacy. This is a technique that is from the house of obfuscation technologies, and it reduces the likelihood of identifying an individual whose data has been included in the training of a machine learning model. This means what can be learned about individuals in the data set is restricted. This method relies on adding noise to the different components of the system. The con is, well, you're adding noise. No data scientist likes that per se. And furthermore, there's a budget associated with differential privacy that limits the number of times a data set or a model artifact can be reused for training or querying. Next, we have secure multi-party computation, which is a collaborative computation methodology that allows participation without exposing an individual node's contribution. The solution restricts what can be learned from the trained pipeline. In some ways, it protects the IP of the individual nodes, but not revealing what came from whom. The con is that it introduces a lot of computational complexity. Homomorphic encryption is an encryption technique that allows performing calculations on top of the data without needing to decrypt the data. This allows access control not only on data at rest and in transit, which are the historic ways of protecting data in computer software, but also during computation and during mathematical operations. This also allows access control on all the artifacts that come out of the system: models, parameters, all of those have the same access control because the data was encrypted. I want to today introduce you to a product we have developed, Powerflow. Powerflow is an end-to-end product that allows users to train privacy-preserving machine learning on top of siloed data using federated learning and differential privacy. We're still in early stages of our product, and we have chosen these technologies to allow an end-to-end solution for cases where data cannot be accessed in a central fashion, and the output of the system contains sensitive information. This enables use cases that require large volumes of patient data, like precision diagnostics and targeted drug discovery, where data cannot be centralized and the information needed is super sensitive. Let's talk about precision diagnostics for a second. Precision diagnostics needs data on medical and social determinants of health to identify patterns that enable physicians to help accurately diagnose and treat diseases at an early stage. Particularly with the rare diseases, any individual institution on their own will not have enough patient-level data to be able to train these models, and that is where Powerflow can help. Another example is drug discovery, because drug discovery identifies opportunities to develop targeted therapeutic based on research in patents, chemical properties, and patient data. This requires large data sets of patients' biomarkers and medical outcomes to target drugs to different patients or identify the right patients for clinical trials. I would like to walk you through a demo, but before I do, I want to make sure that if you take anything away from us today is our 3 differentiators. Trusted performance means that we basically give the users tools to make distributed machine learning as effective and safe as centralized machine learning. Our system is easy to use because we have abstracted away the complexity and we actively integrate into natural workflows of our users. Collaboration, because we know no data scientist can do this alone. These multi-collaboration projects basically need an effort from multiple personas within an organization to take off, and we care about making that easy. Great. With that, I want to basically move to showing you our product. In this demo, I'm going to be playing the role of a data scientist who cares about being able to identify cancer on top of patient-level data, but my patient data is trapped in a few different environments, and I cannot get access to it. Imagine these environments can be hospitals, can be other research centers that I collaborate with. So I'm going to be playing 2 roles here. I'm going to play the role of the data custodian and show you how they can participate in the training. And I'm also going to show you how Powerflow enables them to be able to see information that they need. I'm also going to be talking from the view of the data scientist who needs to be able to modify models, do different things to the data to be able to actually train a model. Great. With that, remember that the federated learning system had a central server that was aggregating the federation. When the machine learning scientist, in this case me, wants to submit a job, it's basically submitting the job to that server. That server is managed by our platform. I'm just going to make an assumption here about a few parameters. This is where I'm going to set parameters such as number of rounds, which basically says how many times the central server should be talking to the nodes, and the minimum number of data sets that are needed to participate. Then I'm going to go and grab something that should look very familiar to the data scientists. I'm going to grab my data description. In this case, I'm using one of our quick start examples, but you can imagine that this is basically the different features related to a patient, can be blood pressure, the time that they visited, so on and so forth. And the target is what the outcome that I'm trying to predict, so the diagnostic that I'm making. This is in the hands of the data scientist. This is where the data scientist forms their machine learning task, and this is where they shine. I'm also going to grab a configuration that is also available in our quick start. And this is where the data scientist is able to define their model, play around with the different parameters that exist in it. The other thing that we expose here is the differential privacy parameters. Basically, how much noise should be added for this to be protected enough. We've abstracted away all the complexities that come with the development of the differential privacy and give the right knobs to the user to be able to adjust. Great. Now I'm ready to confirm my session, and I'm ready to create my session. Once the session is created, I'm going to go ahead and start it. The starting of the session gives me now a unique ID. You can see my ID here. This is all that my data partners need to be able to connect to this training. What you didn't see is that once I created the session, all of my collaborators who have already been invited to the platform received an email with the data configuration that I asked for. I have already gone and created those data configurations, but you can see that that's a job that a data owner can do offline. And then basically run the client software that Powerflow provides to make that data available for the training. All they need to do is refer to the session ID that you just saw, and then run the one command, which basically says train the data on that data set that I created. I'm going to do the same thing for the other data silo. And with that, that's all that the data custodians need to do. The federated learning system is now running in the background. You're going to see logs of the silo shortly that it's connected to the central server. The server is an ephemeral infrastructure. It only gets created for this one session, and then everything related to it gets deleted other than the models. And the only thing that is moving around is model parameters. This is going to take a while, so I'm just going to walk you through our previously run results so that you can just see what is shown on the page to the user. So every round that happens, and this is every communication between the central server and the nodes, the user, being the data scientist, sees the information about the data custodian that has joined, information about their data, and information about the accuracy of the model on top of those local data sets. And this way, they can see whether the model is converging, where are things going wrong, are there data sets that are actually making performance worse so that they can make modifications to the next round. And once this is all done, the model is available to be used for someone with just one command, where they specify the session ID related to that model's ID, and then they're ready to go. Great. You are now introduced and familiar with Powerflow. I'm going to come back to the presentation. So I want to anchor us back in the 3 takeaways that I wanted everyone to remember. So trusted performance. We basically showed you how our system allows an end-to-end infrastructure for federated learning, where the user does not have to worry about operationalizing it, but can trust that the system is valid and good. We have built-in privacy technologies that allows the user to maintain the privacy of the data sets. And we've actually given them also monitoring capability to monitor the performance. The system is easy to use. You saw that the data owner can just join a session with just 2 very small commands. And there's a very small number of steps that are outside of a normal workflow for a data scientist to be able to get a machine learning model up and going. We are still working on our collaboration aspect of the product, but you could see that there is notification admins tool that allows users to add collaborators, and for those collaborators to get notified about the right information that they care about. As part of our future roadmap, under privacy, we care a lot about making the privacy understandable. We talked in this presentation, I talked a lot about how a lot of these privacy toolings are very context oriented. And we want to enable users to make the best decisions for the regulations and constraints of their industry, and for them to not to have to worry about understanding the detail of technology. We'll take that. The onus is on us to figure that out. The system is easy to use, and we're constantly making it easier by integrating into the natural workflows in our future releases. And we're going to add a very project-centric view such that all the stakeholders, like the project lead, like the compliance officers, can participate in making sure that this creates a safe sandbox for the data scientists to become unleashed. The last thing I want to leave you with is that we have an early access program. If the things that I said were interesting and resonated today, please do sign up. We do have a 30-day free trial that allows you to test the environment and see if this is a relevant tool for your use cases before having to turn into paid. Thank you.
Amazing, Ro. Thank you so much for sharing this incredible information with us. I know this audience is going wild with virtual applause.
Thank you.
Thank you. We really appreciate your time today. And for the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and take some time to check out our amazing exhibits. Thanks so much, and we'll see you around.